book on this subject with Christophe Clanet, my friend. And so any subject is fair game. But so we'll be looking specifically at the dynamics of sports balls. But we're interested. But this is just a kind of a fun slide. But it turns out the word religion comes from the French relier les gens, which means to link together people. And of course, in modern culture, football is one of the things which does precisely that. And it is very interesting when you see a small child chasing after a ball, because they seem fascinated by it. I don't know whether it's because we've evolved from hunters or what, but there is something very, very human in the act. And so football has evolved in many different cultures. So there are traces of it in China, 5000 BC. The ancient Greeks, the Japanese, all had versions of the game. But so the first thing I ever asked was, when I was a kid, I spent all of my time playing soccer, and I thought, I realize now in hindsight, this was a scientific question. Why doesn't the thing just follow why does it go like this sometimes? Why does it go like this sometimes? Right? And as a side note, I got interested in science. Basically, I wasn't that interested in science. I just liked playing soccer, and my parents were academics, so I thought, well, might as well study. Seems like a sensible thing to do. I was never really that interested in science, but then I went to university, and because of this question, there were a number of physical things. I wanted to understand how the physical world worked. Why does the soccer ball bend? And I went and studied physics, and after 4 years of physics, I had no idea. Right? We didn't do fluid mechanics. We did quantum mechanics. And so then I discovered fluid mechanics, and through fluid mechanics, you learn how a soccer ball bends, as well as all sorts of things. So then I actually got into science, but it was perhaps in an unusual way. So we know if we launch something at a speed u naught in a gravitational field, we can express the range in terms of its angle of takeoff. So this is a parabola. So this is, again, sort of what we learn in school. And this was studied actually by Galileo. Galileo was his most important contribution in science, and there were many, was his appreciation of experiments. So he did all sorts of experiments, balls rolling down ramps and so forth, and really learning, made clear the importance of observation and experiment. And this is something which the ancient Greeks seemed to be above, and they liked to sort of hypothesize and come up with theories and didn't want to sully their hands with observations. So he's a real hero of mine, Galileo. Okay, but you would think, so let me just go back for a second. So here are some trajectories. I don't know whether these are theoretical or experimental, but there are many situations where things are not a simple paraboloid, as parabola, and here are some examples. So if you hit the ball really hard, this is, by the way, this is supposed to be the hardest shot in history. But watch, he really does belt it, and it seems just to go on a straight line. Watch this. It's got a bit of backspin on it, right? Which will give it some additional lift. And there are other situations where it's obvious. So then you say, oh, well, that could be a beginning of a parabola, and then it's going to turn over. But you also know, when you cross the ball, you slice it, you flatten it, the trajectory, and it drops. So here's another one which is obviously not a parabola. However, you want to look at this one, it's breaking to the left, right? And the one that really got me interested was this one. So this one is like this in the air. So there, and this is exactly the point when I was a kid, shooting the ball with no spin, did you take turns with your friend playing in net, hit the ball with no spin, and you see it goes like this, and I was going, why is that? Are there variations in the atmospheric pressure? What's going on? And so I didn't know, and I went off to study physics at university, and I still didn't know after 4 years. But now I know, so I'll tell you. Okay? So why aren't things following a parabola? So we know we get a parabola if we simply balance the inertia of the ball and gravity. We know that there are additional aerodynamic forces which act on things moving through fluids. Okay? And so this force is, if you're driving in your car, you stick your hand out of the window and you feel a force which is proportional to the cross-sectional area of your hand, your speed squared, and the density of air. Okay? And so this is being felt by the ball as it flies through the air. So there's a force anti-parallel to the direction of motion, which is acting to resist it. Okay, so the question is, when is this important relative to the other forces? When's it important relative to gravity? When's it important relative to the inertia of the ball? So it's important relative to the weight of the ball when this ballistic performance coefficient is small. So again, this is a dimensionless group. We've been doing this in class a lot. So, but we can see these are various ballistic performance. So we can see basketball is heavy. Ballistic aerodynamic influence is very small, whereas football is getting considerable, and ping pong, it's enormous, right? So we all know that you have a massive impact on the trajectory of a ping pong ball by spinning it. And also, if you just think about this, if you have a ping pong ball and a golf ball, they're about the same size. If you throw one, you can throw a golf ball about 80 meters, and you can throw a ping pong ball about 10. And it's because of this. Yeah, try. I mean, yeah. Well, but it's just because of the influence of drag, right? And so you see, and this is the trajectory of this would be a trajectory of a soccer ball. In vacuum, it would go about 100 meters, but because of the influence of the air drag, it's greatly diminished. It's around 70. Okay, so the drag is having a significant influence on their range, and also, so fluid. We know that, and we've seen in the course that fluid can be used for propulsion. So if you're stopping a fluid, there's a drag force. If you're expelling fluid, then there's a thrust, right? So this is the basis of rocketry. You basically shoot fluid downwards, and that gives rise to a propulsive force. This is used throughout nature in a slide which we saw on Monday. So birds fly by flapping fluid, throwing fluid backwards. Similarly, fish swim, and things walk on water by throwing fluid backwards. Okay? So a soccer ball is basically, as it flies through the air, it's deflecting the ambient current, right? So there is this drag force, but it's also throwing fluid this way and that. So it's turbulent, so it's very complicated. And so there's fluid being flung this way and that as it moves through the air. And because the direction of motion of this fluid being flung is changing, so basically if it throws fluid down there, there's going to be a force in that direction. If it throws fluid in the other direction, there'll be a force downward. So basically, as fluid is flung back and forth out of the turbulent wake of the ball, it moves in response. So another way to think about this is that these vortices here represent regions of low pressure because they're regions of high speed. Okay? So as these vortices move up and down on the ball, the pressure distribution changes. So the pressure distribution is the force per unit area, and you get the force on the ball by integrating that force over the surface of the sphere. So basically, as this changes in a random way, the wake of the football changes in a random way, there's a random force being applied, and that's why it will move around like this. So if you hit a ball with no spin, it's basically random what happens here. You can make it coherent by applying spin. So by applying spin, you make it coherent, and you get rid of this random fluttering motion. Okay? Okay, and so that allows us to understand this, right? Where you hit the ball, it's basically you can see it has no spin, and it's it's moving in response to the pressure distribution in its wake. Yeah? What, are they showing the whole game? All right.
La foglia secca.
Foglia secca. Not quite. No, exactly. So, right. So we're going to go through some of the basics. I'm trying not to get too technical, but we basically want to understand drag, concepts of drag, and what the influence of spin is on ball in flight. And then there's some other sort of quirky things which we'll mention at the end. But this is the basic pictures I want you to understand. So what happens when you just have a ball flying through there, and what happens when we have a spinning ball? How is it different? And basically, how do we rationalize that which we see in a football match? So the governing equations for the flow in the air are the Navier-Stokes equations. So U is the velocity field, P is the pressure, and we have a no-slip condition on the surface of the sphere. And we've seen in class, so I can say we've seen in class for those of you who are in the class, that we can calculate the force on the body, on the ball, by integrating the normal projection of the stress tensor over the surface of the sphere. So this stress tensor depends on the fluid pressure and the velocity field. Okay, so in principle, if we know the flow over the ball, we can calculate the force on it, right? Okay, and so there are two different components of drag. So this is the one that I've mentioned. This is the dominant one. Is we have a force which is proportional to the speed squared in the cross-sectional area. But there's also a viscous drag. Okay, and so this viscous drag you get by integrating a viscous stress over the surface of the sphere. And we've done this many times in class. This is the characteristic viscous stress in the system and the characteristic area. So we can assess the relative. So this has to do with the fact that there's dissipation in the system, right? The fact that you have viscosity here giving rise to boundary layers, shear, and there's an associated dissipation. Okay, so the relative magnitudes of these two drag components is prescribed by the Reynolds number, which we've seen many times in class. And we know if the Reynolds number is low, then you get a drag which goes linearly with the velocity, whereas at high Reynolds number, the drag goes as u squared. Okay? And so if you look at the character, so this is basically saying how important is inertial drag relative to viscous drag. Okay, and so if we look at all of the sports balls have very high Reynolds numbers. Okay, but there are changes in the flow as we increase the Reynolds number, and so the nature of the flow changes. In particular, we'll see that turbulence comes in at a certain stage, and this changes things qualitatively. Okay? But in any case, we see that the Reynolds number of soccer is the highest, and things go down to 73,000. But still, everything's basically dominated by aerodynamic drag. So this is the relevant drag for ball games. Okay, so it turns out that if you throw viscosity out completely, then you get into trouble. Okay? So you would think, well, the Reynolds number is that high. It's 500,000. Let's just ignore viscosity. But when you do that, you get into trouble. This was a source of a paradox for some time, D'Alembert's paradox. So this is if you look at the governing equation for the fluid. This, by the way, is simply a continuum statement of Newton's laws. It's saying the force acting on a parcel of fluid is, so this is the mass times acceleration term. A parcel of fluid moves in response to pressure gradients and viscous stresses. Okay? So if you throw out viscosity completely, then, and if we have a steady motion of a sphere, then you see immediately that Bernoulli's equation holds. So that being the case, you can calculate the pressure as a function of the local velocity. So if we have a flow coming in here, we know that there has to be a stagnation point there, which means there has to be local high pressure here. And as it comes around here, it gets fast again, so the pressure goes down. But then it comes down and it's symmetric, and so we have another stagnation point here and high pressure here. So that means we have a symmetric pressure field. So if you neglect viscosity, you get a symmetric pressure distribution around the ball, and so there's no drag. Okay, so this is bad, right? It says, so this is D'Alembert's paradox. You cannot, if you look at motion of an object through an inviscid fluid is actually more general, you get zero drag. Okay? And so we can't neglect viscosity entirely. We have to take it into account, although we know that its effect should be small relative to inertial drag. So how does it come in? So it comes in in these boundary layers. So we know that on the surface of a ball there's a no slip condition, which means that the fluid has to move with the same speed as the object. So basically, as the flow sweeps over the ball, it's locally fixed. So this is flow past a plate, but then it quickly accelerates up to the ambient speed once it gets outside of this boundary layer. So this boundary layer is the region, by definition, is the region in which viscous effects are important. Okay? And so we can, so we're comparing the inertial term and the viscous term. So we can say just by scaling when one becomes important relative to the other. So when does this become important? This is going like del squared. So that brings down 1 over delta squared. And so from this simple scaling, you can see, and this is a general result, flow past anything at high Reynolds number. The boundary layers are going to scale like the body size. So A is basically the size of your ball divided by Reynolds number to the 1/2. So as Reynolds number gets higher and higher, the boundary layer gets thinner and thinner. Okay, so again, so if we think about this, so where is viscosity important in flow past a soccer ball? We put in Reynolds number of 400,000, and we find that it's very thin. It's a fraction of a millimeter, right? So it's about 100 microns. But so this does give rise to some drag, right? So there's an associated shear in here. So there's an associated viscous stress applied to the solid. And this is called skin friction. So we can integrate this stress over the surface of the sphere, and we get a drag. So the drag is non-zero, which is good, but it's nothing compared to the aerodynamic, to the inertial drag, the rho u squared drag. Question?
This is still a viscous drag. So how do you calculate the inertial drag on the ball?
So exactly. So good. Exactly. So we're going to get to there right now. So, but this gives rise to a non-zero drag, so it gets around D'Alembert's paradox, but it doesn't give you the right answer, right? Because if you integrate this over the surface of the sphere, you get something which is ridiculously low. So what actually happens, this is what happens. So it actually changes the nature of the bulk flow around the ball, okay? So, and this is kind of a subtle thing, but I think it's worth going into, because a lot of things follow from this. You can understand, for example, all of streamlining in sport follows because of this physics. So it's worth delving into. Okay, so if we have now a viscous boundary layer, so we've just argued that we have this thin layer in which viscosity is important. So basically what happens is we come in here, we have a stagnation pressure as previously, but now as the flow, so that means the pressure is high, pressure is forced along here, so again, high speed, low pressure here. So we have this pressure gradient along here, which is accelerating the fluid, but it's accelerating less in the boundary layer because you have this viscous resistance, right? So basically what happens, it comes along here, and it's not going as fast as it would be in the absence of viscosity. And so now it's moving, as it moves in this direction, it's moving against the pressure gradient. So the pressure gradient we expect, again, relative like a stagnation point here, so relatively high pressure. So it's moving against the pressure gradient. And because its inertia isn't high enough to carry it all the way back to the stagnation point, it stalls, right? So at this point here, there's separation, okay? So there's a separation point. This is called boundary layer separation. At that point, the flow detaches from the boundary layer detaches from the body, and you basically get a wake, okay? And the key point here is that the pressure in the wake is set by the pressure in the external flow at the separation point. Okay? So we notice that we have low pressure here and relatively high pressure here. So if we can confine the wake to a smaller region, we decrease the drag. The worst case scenario is to have a big wake like this. If you have a big wake like that, then it's all low pressure, which means high drag on the object, right? You want, if you can get back to the potential flow picture where you have a high pressure here, then you have very little drag on the object, right? But basically this boundary layer separation, so the influence of viscosity is not its principal influence is not to give rise to the skin friction, it's to change the bulk flow. So it basically causes boundary layer separation around bluff objects, and as a result, you change the pressure distribution in such a way that you get the rho u squared drag. Okay?
So that's interesting, because that means that still with an inviscid model,
Yeah.
you can cook up this structure by putting two vortices by hand with complex variables. You
Right.
cook this,
Yeah.
and then if you compute the net
Yeah.
pressure, probably you would get something pushing
Yeah,
against.
yeah, it is interesting because you can get a lot of these problems using potential flow theory, but of course the whole reason you have vorticity is because of
friction. But then
viscosity, right? So you're basically artificially cutting
put
it.
the vorticity by hand to compensate for the
Yeah,
it doesn't have
yeah,
to.
yeah, yeah,
That's
Yeah.
interesting. That's actually
yeah,
simple.
yeah. And so, right, so you see basically, so viscosity is hugely important. It's viscosity that gives rise to the rho u squared drag, which is sort of funny, right? Because you get a drag which is rho u squared air, but it doesn't even have viscosity in it, but it wouldn't exist if viscosity weren't there.
It changes the structure, right?
Yeah, because it changes the nature of the flow around the object. Okay, so again, you get this huge, so let's call it form drag or inertial drag.
I have the same exercise in my fluid course. Thanks so much.
And the key thing is to realize that again, the pressure in the wake is set by the pressure in the ambient flow at the point of separation. So by controlling this point of separation, you're changing the drag on the object, and if you can diminish the size of the wake, then you decrease the drag. Worst case is a huge wake like that. Okay, so this is the reason that streamlining is so important in sport and in nature. So if you have a bluff body, again, we have the worst case scenario. We have this large, so depending on the flow, we can have this large eddying wake, and we have this massive drag. If we can streamline the body, all we get is this. We basically eliminate this boundary layer separation, okay? And so we get, we just have skin friction, okay? So this, so we can look at the ratio of these two things. The ratio of the drag on a streamlined body to drag on a bluff body goes as Reynolds number to the minus 1/2. So you can see for these high Reynolds number flows, for sports balls, it's again hundreds of thousands. You have a huge streamlining can have a massive effect, right? So by changing the shape of an object, by making it streamlined rather than bluff, you get rid of this inertial drag and increase the efficiency tremendously. And so this is the basis. So early airplanes, these biplanes, so they had, of course, streamlined wings, but they had these guy wires between them. There was more drag on the wires than on the planes, than on the wings, on the airfoil. So for example, these are two objects which have the same drag, right? So you'd think this has a much greater cross-sectional area, so it's going to be huge, but no, it's streamlined, right? So if you can streamline things, you get much more efficient flows, and of course you can learn from nature what the optimal shapes are, right, rather than doing the math. Nature has solved all problems. Okay, so, but this is, again, this is the basis and motivation for streamlining in sport. They're simply, and so even like basically all of the crossbars here are basically streamlined just to avoid boundary layer separation and the resulting drag. Okay, so I've said the relative importance of inertia to viscosity is prescribed by this Reynolds number. What does flow past the sphere actually look like as we increase the Reynolds number? So we've said that the Reynolds number is high, so this is the sports ball regime, but I think it's kind of interesting to look at how things evolve as you increase the Reynolds number. So if we have low Reynolds number flow past the sphere, so if you drop a marble into honey, then you get a symmetric flow. But the dominant stress there is viscous. Okay? Then as the Reynolds number gets up to around 10, you get boundary layer separation for the reasons we just went through. And so you have an associated drag, which is basically rho u squared. And then around 30, you get this pair of vortices goes unstable, and they start oscillating. And so when that happens, you get periodic vortex shedding. So this is the von Karman Street or the Boulevard Bénard, and this allows you to rationalize some things which we've discussed in class, in particular bubbles in champagne. These are bubbles in champagne. So the Reynolds number of a bubble in champagne is around 10, so it goes in a straight line. But bubbles in beer are around 50, and so they have an unstable wake structure. And so again, as this moves like this, the pressure distribution within the fluid changes, and so the bubble starts wobbling. So you'll see a beer bubble will actually spiral as it rises, and so basically from the motion, you can infer what the Reynolds number is, right?
This is homework for Carnival.
Yeah, exactly, Carnival homework. And so similarly, so bubbles in beer and also fireworks. When you see fireworks, they will oftentimes go like this, and this is again because of the aerodynamic stresses applied to the object in flight. Okay, and so then as we increase the Reynolds number further, you basically get turbulence being generated, so this wake becomes highly unstable. You have this turbulent wake, and then above 2,000 you have this worst case scenario, which is very high, very broad wake, which means very high drag. Okay? And so, but then it turns out, if you go up to higher Reynolds number, depending on the roughness of the object, you trip turbulence in the boundary layer. Okay? And we're going to go through that, and that turns out it decreases the drag. Okay? And you can see why, because again we're confining the area of the wake, right? And we're increasing the pressure in it, because again the worst case scenario is here, where you have separation here, separation at the edge, where the pressure is lowest, so you have the largest area, low pressure wake. Okay, so and this transition. So this transition actually happens in soccer during the course of a single shot. So what happens as we go from here to here? You basically excite turbulence in the boundary layer. So what does that do? So again, we have flow streaming by here. If you have turbulence in the boundary layer, it basically mixes down momentum from the stream. Okay? So it mixes down momentum, so it delays the point of separation. Okay? So imagine you have a stream flowing in this direction. You put dye on the surface. If it's laminar, it just keeps going. If it's turbulent, the dye gets mixed down through the fluid. Same thing now. Instead of dye, you put in momentum. So we have momentum from the overlying stream here. It's being mixed down by the turbulence in the boundary layer, so delaying the point of separation. In delaying the point of separation, you decrease the drag. Okay, so
is this like the case of a golf ball, for example?
yeah, so basically most sports balls, as we'll see, have some roughness, and that's precisely for this reason. Yeah, so a golf ball, if you take it goes, I don't know, you can drive a golf ball 200 meters or something, right? 250 meters. But if you made it smooth, you can drive it for like 50. It's an incredible difference, right? So this turbulence in the boundary layer is hugely important. Most sports, I'm not going to do all sports today, but they have regulations on stitching. So for example, so tennis has fuzz on it. If you play with a dead ball, you'll see that it behaves quite differently. They have regulations on stitching in both baseball and cricket, and it's because and it's the stitching which influences this. So the roughness, this is basically promoted in many sports by roughening of the ball, and it is in soccer as well. And we'll come to that. So things behave very differently if you have a smooth soccer ball. Any of you played enough soccer, you'll know that. So, okay. So this transition can be prompted at lower Reynolds number by surface roughness or stitches. Okay, so here's the drag crisis. So these are, again, so as you're anticipating this slide, these are all sports in which the surface roughness is hugely important. So here you have flow past an object, and you're below the transition to turbulence in the boundary layer. As you increase the Reynolds number, you eventually cross it, and you confine the wake. And in confining the wake, you're decreasing the drag. Okay? Okay, so it turns out that you can actually, so by roughening a surface, you can make it go faster at certain speeds. You would think, well, by roughening it, you're going to increase the dissipation within the flow, so it's going to go slower. Not always, because it can prompt this boundary layer transition to turbulence, and so reduce the drag. So because basically, with a roughened, if you have a roughened sphere, this transition to turbulence in the boundary layer will happen sooner. So you decrease the drag sooner, and so you can the thing can actually a rough sphere will go faster than a smooth sphere. Okay, so.
The American expression, what a drag.
Yeah, there we go. Yeah. Okay, so we have. So we've seen dimensional analysis. This is a nice problem for dimensional analysis. You basically have a ball with radius a flying through the air. So we can identify two dimensionless groups. One is this drag coefficient, so it's the drag force on the object relative to rho u squared. Well, that should be a squared actually. And then we have the Reynolds number. And because there are these only two dimensionless groups in the system, we can characterize the system entirely by plotting one versus the other. So we do that, and you have, so this is the drag coefficient versus the Reynolds number. So this asymptotes to the Stokes drag limit. And you see as the Reynolds number gets up around, so again, this is a sports ball regime around here, you prompt the drag crisis. So that corresponds to the transition of the development of turbulence in the boundary layer. You prompt that earlier with a roughened sphere. So you can reduce drag by roughening. Okay, and so you can ask, well, how rough do things have to be? So you can compare where this drag crisis happens as a function of roughness. And so for a smooth sphere, we see it's here. For a soccer ball, it's here. For a golf ball, it's here. So the rougher it is, the sooner the drag crisis. Okay, now let's look at objects in. I like this. This guy looks tremendously non-athletic. I like that. It's like definitely some Cambridge professor in his backyard, right? So, but you can see there the anomalous curvature of the ball basically bends like this. So he's basically throwing a ping pong ball with side spin, and so it's going like this. Well, yeah, it looks like, I don't know, it's like an ice cream scoop or something. I don't know what it is, but it's like a high li thing. I don't know what it is actually. But here's clear proof that the Magnus effect. So this is the so-called Magnus effect, which causes the lateral deviation. Clear proof that it works is Maradona striking the ball in from the goal line. Right? That was, of course, not the highest quality video, but so this has been studied since. Certainly Newton mentioned it in his writing. So he played some lawn tennis in Cambridge and noticed how the flight of the ball was influenced by spin. Robin was a British artillery sergeant, and he was interested in the flight of cannonballs, so how they would change as a function of spin. So you can extend their range by putting backspin, and change their trajectories laterally by putting side spin on. And this was studied in a quantitative way by Magnus, whose name is now associated with the effect. So he basically looked at the forces on cylinders on rotating cylinders in the air current. And so Rayleigh considered the inviscid theory, and we'll come back to this later. So he showed that if you basically have a spinning cylinder, then the force, so if it's spinning and translating, then the force is proportional to the speeds of translation and rotation. Okay, so this is what you do when you do inviscid theory. Be warned when you do inviscid theory in fluid mechanics. But it's the first theoretical cut at the problem. We'll see that the real answer is much more complicated. Right? And so it wasn't really understood until Prandtl developed his boundary layer theory. So we've basically just gone through the physics of boundary layers, so we kind of know how they work. Okay, so right. So this is the inviscid flow picture of a translating spinning sphere. Okay, so what you do is you say, okay, here's the sphere coming along. We have some flow coming in, and we want to say that the sphere is adding some rotation. So you basically throw in some vorticity in the fluid, and when you do that, then you get this. The streamlines look like this. Right? And so it basically breaks the symmetry of the flow around the sphere, and because the stagnation points are now here, those, again, are points of zero speed and so high pressure, there's an upwards force. Okay, so this is, again, so this is good in that it's consistent with what you know, right? You play tennis, so what are we doing here? We're slicing the ball, right? So in slicing the ball, you're basically flattening out the trajectory, right? You hit the ball with slice, it goes anomalously upwards, right? So it falls more slowly. If you put topspin, you know it dips, right? You slice it, it does the opposite. Okay? And so this is, but again, this is the potential flow. And if you see this and you kind of go, oh, that makes sense. But what are you actually doing here? Well, I mean, what is this? Que hizo? And so, no, this bothered me as a student because you say, oh, now we understand the Magnus effect. No, we don't. Don't understand it at all. How did we've artificially added this vorticity in the ambient flow without saying its origins. It's coming in through the object, right? Inviscid flow doesn't have a no-slip condition, right? That's the problem. So you have to add artificially this vorticity, but it has to come in through the boundary layer. So let's just say we don't understand it yet. But if you do this, the potential, so this is what Lord Rayleigh did, then you find that there's a drag which is proportional to both, there's a Magnus force, this lift force is proportional to both this and this, but we'll see that it can actually change sign, okay, according to the details of the boundary layer, okay? So, but in any case, it is true that the Magnus effect is a consequence of asymmetry in the pressure distribution. So basically, because it's spinning, you're changing the up-down symmetry, so you're getting a lateral force. Okay, that's true, but the details are important. Okay? And in general, this Magnus force is going to depend both on the Reynolds number, which we've seen before, and then this, let's call it a Rossby number. So it's basically the relative magnitude of the rotational velocity, the translational velocity. Okay, so in general, this is the way the forces got to scale, but we still don't really understand it. This is an inviscid flow picture. Okay, so there are applications of this. So ballistics. So if you're on a ship and you're trying to hit a target, when you launch missiles, you usually spin stabilize them to keep them from tumbling. So that basically, then you have a spinning, translating object, right? And it's translating in this direction. So there's going to be some anomalous lift. So when there are people who, so one has to actually correct this. So snipers, if you're shooting from long range and there's wind, they have to know how to calibrate for the Magnus effect on the bullet. Okay, so and some other applications. So there are Magnus sailboats. So these are nice. So instead of having a traditional sail, you have this rotating cylinder, and this is driven by a generator where the energy is ultimately derived from the wind. So they are very environmentally friendly, and they've actually been revived in recent years. So again, you have a spinning cylinder, and wind comes, and there's a resulting Magnus force which drives you along. Okay? And so I think there must have been a mathematician involved because they said n equals, let's do it for n equals 2, and then n equals 3. But anyways, these things do work, and then they're being revived. But more surprisingly is that they've actually made Magnus airplanes. So they actually now have, instead of a traditional wing from which you get lift from the wings are now spinning cylinders. Right? So as this thing moves along with its spinning wings, there's a force which supports its weight. So these things have actually worked, but not very well.
So it can take off vertically, for example?
No, they still have to. They are driven along here, and then but the lift from their spinning wing then causes them to fly. So it's quite remarkable that it ever worked. And this one, so this guy did actually fly once, but then it crash landed. So it works, but the reason, I mean, you can understand why they're not that efficient is that they get their wings are now bluffed rather than streamlined, right? So you get this rho u squared drag instead of right. Okay, so but also the Magnus effect is used in nature. So when you see seed pods flying, so they will. So you can ask. This is something that I was working on with the postdoc Danielle Tam, basically trying to find optimal design. So if you release a seed pod, you want the range to be as large as possible, right? And so it's clear that Magnus effect can help you here, and this is what these things do. So they basically tumble like this. So as they're tumbling, they're moving like this. There's backspin, so you're getting a Magnus lift. So you can extend the range of seed pods. Okay? And this one is a bit patchy, but there is some suggestion that mites, when they leave. What's a mite? Pulga?
So pulga is flea.
But it's close.
It's close.
Yeah. But when they want to maximize their range, and so they jump with backspin, and so you get a Magnus lift. I'm not sure that I believe it, but in any case, so we just did that. So that argument, this sort of picture we had from Lord Rayleigh gave us this drag. So this is the lift. Okay, so this is the lift coefficient here. Okay. Which is in general going to depend on the rotation speed and the Reynolds number of the object, right? And so Lord Rayleigh's theory says that it's 1. So that's what happens when you do that very simple inviscid flow picture that we saw, right? But in reality, we see it has a very complicated dependence on Reynolds number and this rotation. Right? So this is all that inviscid theory gives you. And the reason the inviscid theory gets it wrong is it doesn't take into account the boundary layer. Okay? But when you do this, you see this. You at least get the sign right, which is why this is generally what's taught. But it's not even close to getting the right dependence on the parameters. So, but at high Reynolds number, at low Reynolds number, gets the sign right. Okay. So what I want to note is that this is again Magnus effect. You slice a ball and you give rise to an upwards force, which flattens out its trajectory. But there's also a regime in which the opposite happens. Okay? So this is something, if you've ever played with a smooth ball, if you ever played soccer with a smooth ball, you hit it. So normally you hit a ball like this, you bend it like this and it goes whoosh. But if you play with a beach ball, you hit it like this and it goes in the opposite direction. Okay? And that's because this Magnus force actually reverses sine in a certain regime. Okay? And the reason is this. Okay? So so again, we have a situation where we're slicing, so you expect the thing to get a force in that direction, but because of the asymmetry in the boundary layer separation associated with the rotation, you get the opposite. Okay? Because basically, as the thing is advancing in this direction, the difference between so this is basically the advancing edge. This is advancing and this is retreating, right, because of the rotation. So the relative velocity between this point and the ambient and this point and the ambient is different. So it's higher here. So you basically trip turbulence. So you basically cross the turbulent transition point on one side and not the other. Right? So you get the drag crisis on one side and not the other, which causes, again, a delayed separation of the wake. And so basically fluid is flung out here and you get the opposite force that you would expect. Right? So this boundary layer, so asymmetry in boundary layer separation associated with the rotation can flip the sign on the Magnus effect. Okay? So an important point, so if there were no surface roughening, most sports balls, so again soccer is here, you'd have the opposite curvature. So right. So if we had smooth soccer balls, they would bend the wrong way. Okay. And if you don't believe me, I'll show you.
Which would be like these kids' plastic balls.
Yeah, exactly. Yeah, exactly. But this is a very important point. So roughening not only gets rid of the drag crisis, but it causes things to bend in the way that we know that they do. Right. Okay. So this is again play with a beach ball. You get just the opposite of what you expect. So here, you hit topspin in tennis, you expect it to dip, but because of this asymmetry in the boundary layer, again, it's advancing here, and here it's retreating. So basically the effective Reynolds number is higher here than here. So you get turbulent boundary layer separation and laminar here, and a resulting reverse Magnus effect. Okay, so here we go. Okay, wait. So this is a good video here. So what we did is we took smooth, basically beach ball, right? Perfectly smooth, and we're going to hit it like that. This is my student because I just had a knee operation. So he hits the ball, and then we take exactly the same ball and we just put one elastic band around it. Okay? One. That's all. We'll see what the difference is. So the one with the elastic band behaves normally, hits it like that, and it bends like that. The smooth one goes in exactly the opposite direction. I really like this video. Huh? Cool, eh? He was trying to hit the camera there. Not bad, not bad. Right, so you see smooth, the roughness is very important.
How do you see this ghost effect?
We just have two overlaid. What?
Oh, so there's like two balls at once?
Yeah, the two videos overlaid because we fixed the camera. Okay, and so this is why all soccer balls throughout history have been rough. So they are constantly evolving. In every new World Cup, there's a lot of discussion about the new balls, blah, 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 blah. But there always has to be roughness. If you get rid of roughness, then the things go the wrong way and it's a disaster, right? Okay, so we've seen that the aerodynamic effects are important in determining the range. We've also seen, we mentioned, so the air drag accounts for basically going from here to here, but if we didn't have the drag crisis, then we would only be able to kick about 40 meters, right? So the drag crisis is important also in determining the range. And the altitude is also important because the drag goes as the air density. So when people go and play in Bolivia, or in Mexico City, there were quite a few more goals, and basically the ball is going faster. And you can actually run the numbers. And basically the ball, at Mexico City, the ball will arrive about one ball length sooner than it would at sea level. Okay, so, and the goalie who's trying to stop it, he's not being resisted by air drag, where everything would be the same. He's being resisted by his own inertia, right? He's basically diving. So air drag is not determining his dynamics, but it's determining the ball dynamics. So one has an advantage at altitude. Okay, so now you guys are all going to correct me, except I can blame Andre if you disagree with any of this. So what I say when I speak in countries other than Brazil, I say just as the Inuit, the native Canadian people, have 1,000 words for snow and ice, the Brazilians have an entire lexicon devoted to free kick styles. So here we have so this is sort of the classic one that everyone's familiar with. You hit the ball like this and you expect it to go like that. So we have a nice top corner blast. It's a good one. That's a good one. He's your cousin. So then we have the folia seca. So this is so a little bit of topspin, which is very hard to do, actually, I think. You have very small feet, but here we go. So you can see this does have some topspin. I really dislike this player, but he just takes free kicks. Nice free kicks. Right? See, very, very slight topspin there. But we always come back to this guy. So he's playing for where? Basco now? Yeah. So but there again you can see the nice pure top spin. So when he was playing in Lyon. And I like him because I went to Lyon, I gave this talk, and they wrote a nice article about me. They invited him, but he was in Brazil at the time. But they described me as doesn't get any better than this. The Zidane of fluid mechanics. and he mentioned me in his book, so you can see.
I hope if you're the Zidane of fluid mechanics, I hope at the end of the election don't give me a head.
That's right. It was only later that I realized that he's related to Andre, so I think Andre was probably behind it all. So, okay, and then this is the most colorful name, the dove without wings. So this is basically, again, this is really hitting it with no spin, and so it's going to just move wonkily. I'm not sure if this one actually counts, but I like the goal anyways. But this guy just belts it, and the goalie totally misreads it. But this next one is definitely that. That one we saw earlier by Elano, and also the Japanese goal. This is another. See, it's not spinning at all, really, right? So very difficult to read for a goalie. Okay, and then this is again just classic Magnus, just hitting it with the outside of the foot. There are also interesting questions when it brushes by a player. Because you see sometimes when the ball brushes by a player, it will behave in a peculiar way. For example, here. Because people always say it bent twice, but it also brushed by two players, right? So I'm not sure that that's Socrates, no? Who passed in the ball? And then of course this one. A lot of Brazilians in these clips. I don't know what that is. I'm sure you've all grown up on this one. I remember watching this game when I was a postdoc in England. I was watching it live, and I said to my roommate, I said, have you seen this guy shoot? And he's like, no. And then he scored that one, right? So, but that's not the best free kick. I'm going to show you the best free kick at the end. But okay, that's the second best ever. But you may ask yourself, so why? So every country is known for something. The Brazilians are known for their free kicks, but why are they Brazilian free kicks and not Italian free kicks? The Italians have their own specialty.
Euro 2004.
Any Italians in the crowd? And for our English friend, we have why aren't they British free kicks? So I have a lot of. This is the best. Right, this guy. So this is brutal, right? A penalty shot, and he actually injures himself, right? So there are various possibilities, but it's actually true. So when I went to England and I played, I was sort of at the height of my powers, and I was good at bending the ball. But I went there and I said, the first game I'm on this new team, and they're going, who's this? What's this Canadian guy doing? Who does he think he is? First free kick, I'm like, guys, get out of the way, I'll take this. And I put the ball down, and I'm expecting to bend it in the top corner, hit the ball, and it goes. I'm expecting to do this, and it just goes woof, straight line. I'm like, what is that? Right? So then, 10 minutes later, another free kick. I'm like, guys, out of the way, and they're kind of looking at me suspiciously. Exactly the same thing happened. The ball didn't bend at all. I'm going, what is going on here? So then I had to figure out, well, the Magnus effect is a function of the continent, but No, there are various ways that you can rationalize this. And it is true. I mean, you'll see more nice goals bending shots in nice weather, so in South America than in England, where it's bloody raining all the time and the ball is caked with mud. No, but so it's true. If you have a wet ball, it's harder to bend it. Okay? So this is, okay, that's a question. So the influence of rain on the ball. So basically, it has higher. So the ball is heavier. So it has a higher ballistic coefficient. So it moves less under the influence of anomalous aerodynamic forces, specifically the Magnus force. So that's one thing. So, and it is true. You play with a heavy ball, it's harder to get it to bend, right? But also, the English balls are over pumped. Okay, so the ones we were playing with anyway. So they're basically as hard as a rock, and so the harder it is, it basically decreases the contact time. If you have a softer ball, then you have your foot's on the ball longer, so you can bend it more. So it wasn't. So it took me a while to figure that one out. But anyway, so one can, of course, write down the equations of motion for in principle for a soccer ball, and people have done this. So you write down the trajectory equation, and so then you have this aerodynamic force, which is going to depend on its speed and its rotation rate, right? And so in principle, you can then so you can write these down just from data empirically, and then you can predict the trajectory of a ball. And so people have done this. So you basically use the fluid dynamics. You solve for the flow around the ball, or again you can parameterize this function and so predict the trajectory of a ball. And so they did that with this. So this is a huge. This is the goal that qualified England for the World Cup, and it was like in the 93rd minute. So it's quite a nice goal. So they actually modeled this, but so you basically you can get the initial trajectory of the ball and the initial spin rate, and so you can in principle predict where the thing is going to go. But the question is, of course, what have you learned? And you haven't learned very much.
Or with the fluids model.
This is a fluids model. Yeah. So, but one thing you can see is that so basically as the ball crosses, so it's basically slowing down as it's going through the air, and so basically at a certain stage it crosses this drag crisis. So then its drag suddenly goes up, right? And so it slows down rapidly. And so you can see that the trajectory is slightly different if you take into account this drag crisis. Right? So it is actually important. And Christoph Kleine, who's continuing this work, is looking at the importance of drag crisis, and he's suggesting that a lot of these free kicks, the really tricky ones, are taken just around the drag crisis. So they're actually hitting the ball not that hard, so that it hits the drag crisis sooner. Okay, and so Christoph is a good friend of mine, and he's been really pursuing this work. And this is something that we were looking at what the effect of whether you hit the ball with your toe or the side of the foot, is one advantageous, and for what reason. And it also touches on, so basically, looking at the dynamics of the impact on a ball. And this came up when we were talking about the English balls. If the ball is over pumped, you have less contact time, so have less control. So you can think of the ball as an elastic shell. It has a tension which increases as you pump it up. And this tension also determines the contact time. So these are some photos we took with the Edgerton Center. So basically, again, the side foot of the toe poke. So is one ever advantageous? That's a nice toe poke, huh? Don't try that at home. Pure toe. Okay, but you can actually look at the ball strike. So this is basically the foot speed here. This is the deformation of the ball. So that lasts for 10 milliseconds, during which the foot speed really doesn't change at all, and the ball speed increases dramatically, right? So, so this is quite interesting, I think, because FIFA stipulates a range of pressures within the ball, okay? And there's actually quite a large range. So it has to be between 0.6 and 1.1 atmosphere. Okay? So over this range, how does this picture change, right? And we actually find that the contact time is a function of the overpressure, and it decreases by 20% over the permissible pressure range. Okay, so if you're playing a team with very good players who are good at bending the ball, what you want to do is overpump the ball, right? So you want to make it as hard as possible. Conversely, if you're a skillful team, you want to be at the lower end of the spectrum. Right? Okay, and yeah, so the last thing I was to mention, this is Christoph's idea, which I think is a brilliant idea. This is Perrin, who looked at Brownian motion. Okay, so he basically is looking at how molecules jiggle around as a result of Brownian motion. So dust particles move in response to the random motion of the air in which they're suspended. So basically, if you follow the thing, it moves around randomly, but you can characterize its mean motion through a diffusivity. Okay, so this has units of length squared per time. So that basically gives you the time over which the thing spreads. Okay? And so if you look at a soccer. So this is the trajectory of a soccer ball during a match. So this is Man United versus Liverpool. And you can see it's kind of random, right? It's moving around, but it's not completely random. There seems to be, so if we look back here, you can see that there's a characteristic step length. Right? And there will, of course, be a characteristic speed. And this diffusivity is prescribed by that step length times the speed. So it has units of length squared per time, so you get it by... So D is basically given by the product of this mean length and the speed. Okay? So you can do the same thing in a football match, right? And so so if we look at the trajectory of a ball, basically this is it after a certain amount of time, and one can play the same game. And so you can define a diffusivity, and so the diffusivity basically is going to tell you how long it takes to cross the field, right? So it's basically through this random walk. And so the number of times it crosses the field gives you the number of shooting opportunities, right? And so what is this random walk going to depend on? So it's going to depend on this mean length again, as well as the speed. So the speed is basically the average speed of a pass. But this length is going to be determined by the distance between players, right? So you can actually do the scaling for different size fields, right? So we know on a big field, it's basically going to scale depend on the area and the number of players. That's the average distance. And so you can scale it for 11 aside, 7 aside, 5 aside.
This is probably what model on Barcelona. I don't know a team that can have 7 consecutive passes these days. Huh?
Oh yeah, that's true. No, but it's interesting to look at this, using this as a diagnostic to assess the style of different teams. You know, Barcelona would be a spike, right? They would be an anomaly, and then you'd have some of the Scottish teams.
Everything you say.
Yeah, right. But you can actually evaluate this, and this is not just for soccer, right? You can do this for hockey, you can do this for handball, you can do it for many ball sports in which there's basically a pitch, and so you can actually test this theory. So again, you basically say that there's a diffusivity which depends on the speed of the ball and the average distance between players, which then again is going to scale with the size of the pitch and the number of players. So you can actually get the scaling. Predict the diffusivity, and this diffusivity is going to give you the number of the number of crossing times, the number of shooting opportunities. Okay, so this is we had a student visit. Christoph sent over from Paris, and he worked on this for the summer. And these are the shooting opportunities. So using this simple model of Brownian motion. So for soccer, hockey, basketball, water polo, handball, and lacrosse. And so you can see it gets the trends right? So, I mean, you're going to have some unknown scaling factor, but it basically captures the right behavior. So I just think it's kind of an interesting thing. I like to. Christoph is a very creative guy.
So when a team dominates the game, the diffusivity coefficient goes down because it stays more in one part of the field?
Well, it's yeah.
How do you react to that?
Yeah, so it doesn't take into account asymmetry, for example, right? So, although, yeah, I have to think about that one. Yeah, I'm trying to think in what way Barcelona would be anomalous, right? Because they still do move all over the field, right? It's just because the team possessing the ball isn't in this model, right? It doesn't care who's in. Okay, so right. So, anyways, these are, if you're interested, these are nice reference books. And this is a wonderful, if you like aerodynamic drag, it's a wonderful book by Asher Shapiro. Or if you see some of those, I had some black and white slides that looked like they were made in 1950. Those are all from his book. But he was a great guy. And there's annual reviews on this. This guy's a real sort of guru on drag and boundary layer transitions. And Christoph and I are trying to write this book while I'm here in Brazil. We'll see how it goes. I have some other distractions, but I'm working on it, Christoph, if you're watching. Okay, so here's the greatest shot of all time. You thought it was Roberto Carlos, but there's one that's even better. Another Brazilian. Like this.
Happiness is a cigar called Hamlet, the mild cigar.
Okay, all right. Thanks for your attention. What was that?
Well, you said you were speaking Portuguese, right?
Oh, yeah. Question period. Question period.
Ask questions kind of in the seminar. It was your last class.
Yeah.
It's similar stuff,
Yeah.
so.
Yeah, no, please. If you have any questions?
Comments.
Any questions? Because especially if you have any things that you've thought about in soccer, like funny things that you don't understand, I've probably thought about them as well. So you can bounce it off me. Anything? They only qualified for the World Cup once, 1986. Some of my friends are on the team. There's 1,000 to 1 odds against their scoring. It's pathetic. What's that? Sorry.
The ball must be too heavy.
Oh yeah, no. Well, yeah, it is. They mostly have British coaches, so they never learn how to bend the ball. That's the excuse I use. Yeah.
And when you see the ball brushes like a defender, is there an idea of like how?
Yeah, so
without touching, how close?
yeah, basically it has to be exactly.
The effect of the surrounding flow.
Yeah, so it has to be kind of get within a boundary layer. But you see this sometimes. You'll see balls brushed by a defender really closely and then veer dramatically, right? And they aren't necessarily making contact, but in disrupting the boundary layer flow, you're changing the symmetry of the wake, and so the thing moves in a funny way. And I can't remember. I've seen it several times. But I can't remember whether it goes that way or that way. I think it might be that way.
Well, the Italian one seems to call my attention. It seems like it goes like this near the chest of the Italian defender, and then it goes.
Yeah. So it's unclear because there's also the possibility of contact if it's moving that way. Yeah.
Like a touch, though.
Yeah. But one should be able to rationalize these things.
How would the shape of the boots benefit?
Oh, so that also, you can imagine getting more traction, so more contact. So it's in contact for a longer time, and also getting enhanced grip. So I think those Predator boots. I've never played with those actually. Has anyone played with Predators?
Yeah, there are boots with enhanced grip.
Yeah, that's what they say, but I don't know if it actually works. But you can imagine it would, right? You can imagine getting more contact with more texture, say, especially if you have a wet ball. You know, if you have because it's very easy to sort of scuff a ball if your boots are smooth and the ball is smooth and wet.
One comment I made last time I actually gave this talk here, which is different. We have a lot of new stuff.
I did a remix.
Yeah, remix and new stuff. The last time you were here was before the last World Cup. So the last World Cup, the players were complaining a lot about the Jabulani, right? Jabulani became famous. And the Jabulani is less rough, right?
Yeah.
That's why it's more random.
Yeah.
Right? And before the other World Cup, I think it was a Nike, I think. Jabulani was what? Adidas, right?
Yeah, I think so. Yeah.
And Nike released a ball, but they tested it before the World Cup, so it didn't make it to the World Cup. And the Nike ball before the other World Cup had little dimples as a golf ball.
Yeah.
So it had the texture like a golf ball. And I remember here in Brazil, they had some players trying it out and said, oh, this ball is much lighter than the other one. I don't like it. It's too light. And it was not. It was the exact same weight.
It was a texture that changed
it.
it.
Texture that made it feel lighter and curve less because it had less drag.
Oh, yeah.
Because it had the golf ball effect.
Oh, yeah. So they actually had texture.
It was all full of little dimples around it.
Because they've actually designed.
They took it out of the market.
They've actually designed golf balls. So instead of putting dimples on them, they put bumps on them, and they go 50% further. So it's very, they basically say, okay, how can we optimize this? So they don't exactly know how it works, but it goes 50% further. But if they were going to use those, then they'd have to extend all the golf courses by 50%, right? So easier just to stick with the dimples. But you can see there is, huge effect of the roughness on the ball.
How is the shark skin effect too, right?
Oh, so
it's not structured, but it improves things, right?
Yeah. So sharks. Yeah, they basically there's roughness on a small scale. So, which is definitely drag reducing. Yeah. Yeah, a lot of these same issues, in the course we were talking about water repellency, and a lot of these issues come up in drag reduction as well. But what microscale allows you to reduce drag, and now because they can manufacture things on that scale, they're looking into it. So I think it's a combination there of texture and compliance. So the fact that the stuff can actually move. Compliant, so it's not purely rigid. It's right. So
like there's a fluid structure interaction.
Yeah. And there's talk of in some animals of being polymers released into the fluid, so reducing the turbulence in the boundary layer. All right. Okay. Thanks for your attention. Maybe if the guys in the class can stay around for a second. Yeah.